Millions of tons of industrial cargo traverse the open ocean every single day aboard commercial vessels of staggering scale. If you look closely at the hull of a working ship, you will often see the crew pumping streams of water directly into the sea. While this appears to be a blatant violation of international law, these commercial vessels are essentially floating factories that inevitably generate chemical waste as part of their normal operations. The first source of contamination is the engine room. Here, seawater used for cooling systems leaks onto the deck and collects in the bilge wells, mixing with fuel oil and grease to create a toxic, sludgy byproduct. The second source is the cargo hold itself. To maintain stability during the return voyage, massive oil tankers intentionally flood their empty tanks with millions of gallons of seawater, a process known as ballasting. A ship can neither store this volume of wastewater indefinitely nor dump it untreated. To protect the oceans, marine engineers rely on the manipulation of microscopic fluid physics and rigid global regulations. Oil naturally floats on water due to its lower density, but relying on passive separation is far too slow for a working vessel. To speed up the process, engineers look to a formula discovered in the 1800s called Stokes Law, which defines how particles move through a fluid. Stokes' law proves an oil droplet's rising velocity is proportional to its diameter squared. Combining microscopic droplets accelerates them upward exponentially. Inside an oily water separator, a coalescer forces tiny droplets to merge into large masses, shooting them to the tank's top for extraction. Beyond changing the size of the droplets, engineers can also manipulate the force of gravity. By using high-speed marine centrifuges, crews create an artificial centrifugal force hundreds of times stronger than the Earth's natural pull. This extreme force violently drives the heavier water outward against the walls of a spinning bowl, while the lighter oil is forced into the center to be piped away. By mastering these variables, droplet size and gravitational force, engineers transform a slow natural process into a highly efficient, legally compliant extraction system. Outside the engine room, the challenge shifts from microscopic particles to the massive structural physics of the hull. Tankers are designed for extreme deadweight efficiency. When they unload their liquid cargo, the ship becomes so light that it sits dangerously high in the water. This creates a mechanical crisis. An exposed propeller loses its thrust, putting a destructive, uneven strain on the propeller shaft bearings. To sink the ship back to a safe draft, the crew floods the empty cargo tanks with seawater. However, because those tanks were just holding crude oil, the incoming water instantly mixes with the sticky, toxic residues coating the steel walls. While ballasting solves the immediate physical threat of an unsteerable ship, it leaves the crew with a massive volume of contaminated water that must be resolved before they reach the next port. Releasing this water back into the ocean is governed by strict international mandates that every crew must follow. To legally discharge, a tanker must be moving forward at least 50 nautical miles from shore. Sensors ensure that the oil content never exceeds 30 liters per nautical mile, a concentration low enough to be considered negligible in the open sea. Modern maritime engineering avoids the bulk of this contamination through a process called crude oil washing. By spraying a portion of the cargo back against the tank walls at high pressure, the oil acts as a solvent for itself, liquefying residues so they can be sold rather than washed away with seawater. The ultimate evolution is the use of segregated ballast tanks, which keep seawater and cargo oil in entirely separate plumbing systems. This legal requirement for segregated tanks effectively forced the invention of the modern double-hull tanker, creating a permanent physical buffer between the cargo and the environment. That opening visual of a ship discharging water represents the mathematically verified endpoint of a rigorous decontamination process. While double hulls cannot prevent every possible disaster in high-energy collisions, they have significantly reduced the chronic, daily operational pollution of the past. Through the mastery of fluid dynamics and global legal compliance, the maritime industry continues to balance the demands of global trade with the preservation of our oceans.